conditions when probabilistic analysis may be associated with greater biases than deterministic analysis. This presentation is based on our publication titled as Understanding Bias in Probabilistic Analysis in Model-Based Health Economic Evaluation. I thank my co-authors. In the field of health economics, probabilistic analysis refers to specifying sampling distributions of sample mean as the model input parameters to capture uncertainty around the parameters. Deterministic analysis assigns point estimates to the model input parameters, often represented by the sample mean. Deterministic analysis uses point estimates which are often best fitted with the observed data, maximum likelihood estimation, and represents the best guess for the model input. When the information that the data contain about the parameter is less certain, the parameter estimates may not be precise and thus have a large standard error. In such circumstances, simulated model inputs used in the probabilistic analysis may generate data which are quite different from the maximum likelihood estimators. The expected values of model inputs in probabilistic analyses may be different than those in deterministic analysis. Ultimately, probabilistic analysis in which the model inputs may have smaller likelihood to fit the observed data will not necessarily yield more reliable model outputs than deterministic analysis. We provide an example of treatments for patients with varicose veins. The network meta-analysis showed that the odds ratio of re-intervention for MoCA versus high ligation surgery was 0.46. 95% confidence interval is 0.01 to 29.92. That is, the point estimate of 0.46 was favoring MoCA with a very wide 95% confidence interval. The odds ratio is assumed to follow log normal distribution, and the expected odds ratio in a probabilistic analysis of these data is 3.7. Thus, drastically different findings of the analysis may be arrived at when the model input in deterministic analysis favored MoCA, while the inputs in probabilistic analyses favored high ligation surgery. The results from probabilistic analyses are inconsistent with what is noted broadly in the literature or reported by many clinicians because the risk of neovascularization and reintervention after surgery is generally higher after surgery than endovenous therapy, such as MoCA. Simulations from probabilistic analyses may yield more extreme values that can bias the results in nonlinear models. For example, the expected value of an exponentially distributed random variable x, years of survival, with a constant rate parameter lambda, mortality rate per person year, is equal to the multiplicative inverse of lambda. When the variance is large, data derived from a study with a small sample size, probabilistic analyses can yield some simulations with small values for lambda and can substantially impact the expected value of x. A deterministic analysis using the point estimate of lambda may avoid this problem. Thus, a probabilistic model may result in larger bias in model outputs than the deterministic model. A simulation study compares bias in expected life years in a two-state Markov model in probabilistic versus deterministic analysis. It was a simple Markov model with two health states, alive and dead. Conceptually, this two-state Markov model is approximately equivalent to an exponential survival model with a constant hazard function, but the survival time of an individual is discrete with a fixed interval, the Markov cycle. The results of this simulation study was presented in this table. The bias and mean squared errors of deterministic analysis were smaller than that in the probabilistic analysis, in all three scenarios. When the cohort size was small, n equals 100 in scenario 1, the bias of life years in the probabilistic analysis was much greater than the deterministic analysis, 3.19 versus 1.16. However, when the cohort size was large, n equals 1000 in scenario 3, the biases were much smaller in both approaches, probabilistic 0.19 and deterministic 0.09. We may caution the application of probabilistic analysis under some conditions when deterministic analysis may be more appropriate for these cases. For instance, when the key model parameters have wide, asymmetric confidence intervals, such as odds ratios of clinical effects from network meta-analysis. For another instance, when the variance of a model parameter is large, such as parameter estimates based on data from a small sample size. Here, simulations from probabilistic analyses may yield extreme values that tend to bias the results of some nonlinear models and may not be meaningful. Deterministic analysis can avoid extreme values that probabilistic analysis may encounter and may provide a less biased estimate. Thank you.